Dear students, today we'll see some multiple choice questions on the topic resonance, in which we will cover the concepts of series resonance and parallel resonance. So let's start with the topic DCET or Communication Systems Part 3. Now in this we'll start with a resonance, and let's start with the first question on a resonance. Question number 41. The minimum value of impedance is available on series resonance circuit. So the minimum value of impedance is available on series resonance circuit. So the circuit, when it is series resonant, the impedance which is available is minimum. So is the statement true? So let's see this circuit of series resonance. Say this is your R, this is L, and this is C. So all these are connected to a AC supply where we can change the frequency. So here you can see this. So this is R, this is L, this is C. Now at a resonant, when this input of frequency is at a resonant frequency, at that time the reactance of the inductor and reactance of the capacitor will be equal and opposite. They will get cancelled out, and what remains will be only the resistance in the circuit at resonance. So at a resonance, the impedance Z is equal to only the resistance R. Okay. So it is true that the minimum value of impedance is available on series resonance circuit at that particular resonant frequency. So the impedance is minimum. So here option A is the right answer. So option A, it is true. The statement is true. So here you can see the statement is true. Then we'll go to the next question. The total current of a parallel resonance circuit. Now we know in parallel resonance circuit, when the resonant frequency is there, maximum impedance and minimum current. So if you see the graph of parallel resonance circuit, so here you can see the graph of parallel resonance circuit. Say this is a graph of frequency and current, frequency versus current. So if you see this graph will look like this. So here you can see that at resonant frequency, the current will be, if you speak ideally, it will be zero. The current ideally will be zero. Practically, it will be very low. Okay. So the total current of a parallel resonance circuit, if we want an ideal answer here, then answer will be zero. So it is very, very less at resonant frequency in parallel resonance circuit. So here you can see option B is the right answer here, 0. Then we'll go to the next question. The total current of series resonance circuit is maximum. Obviously, it is maximum because for series resonance circuit, if you see the graph of frequency versus current, so this is current, this is 0, this is frequency. If you see the graph for current, it will be like this. So the current will be maximum at resonant frequency F naught. So we'll be having maximum current here. So I max. So the statement that is the total current of series resonance circuit is maximum is true. Okay, so here option A is the right answer. So here we can see the above statement is true. Then we'll go to the next question. Zero phase angle will be gain of dash resonance circuit. So if we see a series resonance circuit or parallel resonance circuit, at resonance, the voltage and current are in phase. There is no phase angle between the voltage and current vectors. So here, zero phase angle will be gain of dash resonance circuit, both series and parallel resonance circuit. So option C is the right answer here, both A and B, because A is series resonance circuit and B is parallel resonance circuit. So both A and B are the circuits where the phase angle is 0 at resonant. That is, the current is in phase with the voltage. Then we'll go to the next question. The power consumed with series and parallel resonance circuit is maximum. Obviously, when the resonance take place at series or parallel, the power consumption is maximum. So obviously option A is true. So option A is the right answer. Then we'll go to next question. The power factor is unity for the dash resonance circuit. Now for a resonance circuit, the voltage and current are in phase for both series and parallel. Okay. Now that will be the phase angle phi, what will be given. So for series and parallel, this phi will be equal to 0. That is, current will be in phase with voltage. In phase with voltage. Okay. Now we know that power factor is nothing but power factor is the cosine of the phase angle, is the cosine of the phase angle between voltage and current. So that is cos phi. So this is cos 0, and cos 0 is nothing but the value of cos 0 degree is 1, unity. Okay. So therefore the power factor is unity for the dash resonance circuit, that is for both series and parallel resonance circuit, it is unity. So option C will be the right answer here, both series and parallel resonance circuit, both A and B. So here you can see option C is the right answer. Then we'll go to next question. Question of 47. Series resonance circuit frequency formula is. So here if you remember the formula for series resonance, the frequency of a resonance is given as F naught is equal to 1 by 2 pi root LC. So here option B will be the right answer here, 1 by 2 pi root LC. So here you can see the resonant frequency of series resonance circuit is 1 upon 2 pi root LC. Then we'll go to the next question. The total reactance of a series resonance circuit is 0. Obviously, the total reactance, that is opposition to the flow of current due to capacitor and inductor, will be 0 because they will both equal and opposite, so it will be 0. So here option A will be the right answer here. It is true. So option A is the right answer. Then we'll go to the next question, question number 49. The total susceptance of parallel resonance circuit. So obviously when we define the parallel resonance circuit phenomena, at that time we say the susceptance of inductance and a capacitance will get cancelled out. So it is equal, and therefore the total susceptance of parallel resonance circuit is minimum. Okay. So minimum means less current is going to flow at resonance for parallel because the impedance will be maximum. So the total susceptance of parallel resonance circuit is minimum, and ideally it is 0. So option C is the right answer here. Ideally it is 0. So here you can see the total susceptance of parallel resonance circuit is 0. Then we'll go to next question. In the parallel resonance circuit, the effective impedance is equal to what? Now, after we do the analysis in parallel or resonance circuit, the effective impedance, what we see, will be given as L upon CR, and this statement is true. So option A is the right answer here. The effective impedance of parallel resonance circuit is L upon CR. It is true. So option A is the right answer. Then we'll go to the next question. The effective impedance of series resonance circuit is equal to how much? Now we know that in series resonance circuit, the reactance of the inductor and capacitance will be equal and opposite. They will get cancelled out. So for series resonance circuit, the effective impedance will be the resistance R itself. So only R remains in the circuit. So here option D will be the right answer. That is, the effective impedance of series resonance circuit is equal to the resistance R. So here you can see option D, R is the correct answer. Then we'll go to next question. The series resonance circuit increases the voltage of the circuit. Obviously, the series resonance circuit increases. It is going to increase the voltage of the circuit. So option A, that is, it is true. The above statement is true. So here you can see the above statement is true. Then we'll go to next question. Quality factor Q of a circuit is also known as figure of merit. Obviously, the quality factor Q, which is a reactance upon resistance, which can be XL upon R or which can be XC upon R, is also known as figure of merit. So this statement is correct. So option A is the right answer. It is true. Then we'll go to the next question. If the value of C in a series RLC circuit is decreased, the resonant frequencies. So if you see for series resonant frequency, if you see the formula is 1 upon 2 pi root LC. Now if the value of C is decreased, if the value of C is decreased, okay, then automatically, because the resonant frequency is inversely proportional to the value of C, the value of resonant frequency will increase. It will increase. So here, out of these options, option B will be the right answer. It increases. If the value of C in a series RLC circuit is decreased, the resonant frequency increases. So here we can see option B is the right answer. It increases. Then we'll go to next question. In a series RLC circuit that is operating above the resonant frequency. So when the series RLC circuit is operating above the resonant frequency, the current is, the options are lags the applied voltage, leads the applied voltage, is in phase with the applied voltage, or zero. Okay, so if the resonant, if the frequency is above, the operating frequency is above the resonant frequency, then in that case, the current lags the applied voltage. So option A will be the right answer. So here we can have lags. And if it is below the resonant frequency, if the operating frequency is below the resonant frequency, then it leads the applied voltage. If it is exactly as the at the resonant frequency, then the current is in phase with the applied voltage. Okay, but in this case, when the series RLC circuit that is operating above the resonant frequency, the current lags the applied voltage. Then we'll go to the next question. The impedance at the resonant frequency of a series RLC circuit with L is equal to 20 millihenries, C is equal to 0.02 microfarad, and R is equal to 90 ohms is how much? So we know that the impedance of series resonance circuit at resonance will be only the resistance itself, because the reactance of inductor and capacitor will be equal and opposite, they will get cancelled. So here R is equal to 90 ohm given in the question. So option B, 90 ohm, will be the correct answer because it will be only resistance R. So here option B, 90 ohm, is the correct answer. Then we'll go to the next question. A 24 ohm resistor, an inductor with reactance of 120 ohm, and a capacitor with a reactance of 120 ohm are in series across 60 volt source. The circuit is at resonance. The voltage across the inductor is how much? If we are having this series resonance circuit, now this will be the series resonance circuit, and this will be the voltage source which is applied across this. So this is around 60 volt. Okay, and this resistance is 24 ohms, and the reactance of this inductor is 120 ohms, and the reactance of this capacitor is 120 ohms. Okay, so at resonance, when the voltage is applied, the current which flows here, current I, okay, the current I will be obtained by only the resistor in the circuit, because the reactance of inductor and capacitor will get cancelled out. So the current is given as I is equal to 60 upon 24. So here 60 divided by 24 is nothing but 2.5. So the current is 2.5 ampere. Now that current multiplied by the reactance of the inductor will give you the voltage across the inductor. So here, if you take the voltage across the inductor, current multiplied by the reactance of the inductor, that is 120. This is nothing but 300 volt. So option D will be the right answer here. That is 300 volt will be the voltage across the inductor at resonance. Okay, so here option D is the right answer. So here you can see option D is the right answer, 300 volt. Then we'll go to the next question. Capacitive susceptance is a measure of what? Options are a purely capacitive circuit's ability to pass current, purely a capacitive circuit's ability to oppose or to resist the flow of current, the extent of neutralization of reactive power in a circuit, reactive power in a circuit. So obviously, when we say it is susceptance, it is the amount of allowing ability. So when a capacitor circuit's ability to pass current is measured, it is nothing but capacitive susceptance. So option A will be the right answer here. A purely capacitive circuit's ability to pass current is known as susceptance. So here you can see option A is the right answer. Then we'll go to next question. The a current through a series RLC circuit under a resonance condition will be how much? V upon R, V upon XC, V upon XL, none of this. Obviously, at resonance in the circuit, we'll have only a resistance because the reactance of L and C will get equal and opposite are cancelled out. So the current flowing through the circuit will be nothing but voltage upon the resistance of the circuit. So it is V upon R. So option A is the right answer here, V upon R. So option A, V upon R is the correct answer. Then we'll go to next question. At a resonant frequency, an RLC circuit draws maximum current due to the reason. The option says that the difference between capacitive reactance and inductive reactance is zero. This is the correct answer because the inductive reactance and capacitive reactance will be equal and opposite. So the difference between them will be zero. So there will be only resistance in the circuit, and because there is minimum impedance in the circuit, the current which flows in the circuit will be maximum. So at resonance, an RLC circuit draws maximum current due to the reason that the difference between capacitive reactance and inductive reactance is zero. So option A is the correct answer here. So here you can see option A is the right answer. Thank you, students.